We just finished an introduction to the concept of differential equations. The goal of this series will be to learn about all the different types of differential equations and how we can solve them. Just like how in algebra there were lots of types of equations: linear, quadratic, rational, trigonometric, exponential, logarithmic, each with a different way to solve it, differential equations also require different methods depending on what they look like. So the first thing we'll need to do is learn how to classify differential equations. While algebraic equations that we all know and love have an unknown variable to be solved for, differential equations have an unknown function, expressed in terms of its derivatives. While this may sound intimidating, if you already know how to work out indefinite integrals, then you have already been solving a simple type of differential equation in disguise. For example, the integral of x squared dx is another way of saying dy dx equals x squared. This is a differential equation. Here we are asking the question, what function has a derivative that's equal to x squared? Recalling that the opposite of differentiation is integration, we can get the answer by integrating x squared, which will lead to the solution of the differential equation, y equals x cubed over 3 plus an arbitrary constant. Not all differential equations can be solved so easily, and we'll need some new terminology to describe all the types of DEs that we could possibly encounter. The dependent variable is what we want to solve for. In the previous example, that's the letter y, which was a function of x, which is the independent variable. We say that a DE is ordinary if there's only one independent variable, or partial if there's more than one. In this series, we'll start with ordinary differential equations, or ODEs, before moving on to partial differential equations, or PDEs. We say that a DE is linear if the dependent variable and its derivatives are just by themselves, with no exponents or functions. If there are, then the DE is nonlinear. If the DE is linear, then we also say it is homogeneous if there are no terms with just the independent variable or a constant on its own. If there are, it's nonhomogeneous. Next, the order of any DE is the highest derivative present, and the exponent on this highest derivative is the degree. Lastly, autonomous means that the independent variable doesn't appear anywhere except as a derivative. For example, dy dx plus y times sine of x equals 0 is ordinary, linear, first order, first degree, homogeneous but not autonomous, and if the right-hand side became any other constant or expression of x, it would become non-homogeneous. Now that we know how to classify a differential equation, let's talk about what we can expect to get out of them. As mentioned, the goal of solving a differential equation is to solve for the dependent variable, such as y, which is really a function of the independent variable, such as x. If we can achieve this so that we get our answer as an expression in the form y equals some function of x, then we call this an explicit solution to the differential equation. Sometimes, however, we will find that the best we can do is find an algebraic equation relating x and y, which can't be rearranged to express y in terms of x. We would call this an implicit solution. The differential equation we solved at the start, dy dx equals x squared, had a solution y equals x cubed over 3 plus a constant c, and this is an explicit solution. You might be wondering, what is the c in this answer? Back when we learned about indefinite integration, we would often just put this plus c on the end of any answer we got and leave it at that, but now we can actually put it to some use. In the language of differential equations, if we find that our answer contains an arbitrary constant like this, we call it a general solution. A general solution represents a whole family of solutions because that constant could be anything, and each one is a different function, all satisfying the same differential equation. If we want to narrow our family of solutions down to one particular solution, we need to constrain our general solution using boundary conditions. Boundary conditions are simple equations that tell us key information about the solution that we're looking for. A common type of boundary condition is an initial condition, which just tells us the value of the function at some point. For example, if we have the differential equation dy dx equals x squared, and we are told that the value of y at the point x equals 0 is 1, then we can use this to find the unknown constant c. Starting with our general solution, y equals x cubed over 3 plus c, we can substitute in x equals 0 and y equals 1 to get 1 equals 0 cubed over 3 plus c, which simplifies to 1 equals 0 plus c, giving us c equals 1. We say that the particular solution to the differential equation dy dx equals x squared, satisfying the initial condition y of 0 equals 1, is the function y of x equals x cubed over 3 plus 1. The number of boundary conditions required to completely whittle down a general solution into a single particular solution is equal to the order of the dE. Intuitively, we can think of repeatedly integrating the differential equation, each time reducing the order by 1 until all the derivatives are gone, at which point we will have generated that many different plus c's, which each require one boundary condition to be found. As always, math is not a spectator sport, so let's get some practice by checking comprehension.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.